Hi everybody, this is Aaron Murakami with eMediaPress.com and the Energy Science and Technology Conference. And today is January 13th, 2021. And we have Jeremiah here, who some of you saw at the conference. And you want to tell everybody what your website is?
iEnergySupply.com.
And how can people support your work with the Tesla Turbine project?
Patreon.com is probably the best place. Is the best place to support us, because if people have questions and if they want updates on the project, they can. There's 3 different tiers. There's general updates on the project. There's behind the scenes, and there's also CAD drawings.
Now, is there a link on iEnergySupply.com to your Patreon account?
I think there is.
Okay. And is there also a
Patreon.com/iEnergySupply will take you straight to the Patreon.
Okay. And do you also have like a PayPal donate link on your website, or?
I actually set up a PayPal donate link.
Okay.
And there was some details in there that we were supposed to fill out. Okay. And we were never able to actually fill them out. So
okay. So no PayPal.
PayPal actually was like, okay, yeah, here's your link. Mm-hmm. And then we were sending people to that link, and no money was showing up. We had several people put money into our account, and then it went into random charities, basically.
Okay. And then you also have a Facebook page.
So that no longer works.
Okay.
But we will set one up that will work. But right now, if you want to donate to PayPal, it's orders at iEnergySupply.com for PayPal.
Okay. And then you also have a Facebook page. People can type in iEnergySupply and your name, and that'll bring you to your PayPal page. And of course, you have a YouTube channel.
Yep.
And then, so we're here in the Inland Northwest, up here in the Spokane, Washington area at our shop. This is where we put together the multi-wave oscillator units and have some other projects with Eric Dollard and some other people going on here. And what we're going to do right now is Jeremiah is going to explain what's sitting on the bench in front of him, and he's going to give a walkthrough of the general principles of how the Tesla turbine work, 2-stage one with a drive stage and a pump stage. And then he's going to assemble this one. Yep.
Okay, so basically the principle behind using a pump with the turbine is the reduction in back pressure. And there's videos on YouTube that will give you a really good visual of why that's important. If you type in supersonic ping-pong ball on YouTube, they use a vacuum tube, or they use a vacuum to evacuate all the air out of all the atmospheric pressure out of a tube, and then they put the ping pong ball in one side, and then they puncture the diaphragm, and then ambient air rushes in the vacuum and pushes the ping pong ball through the tube, and the ping pong ball can actually reach supersonic speeds. And normally you can't get a ping pong ball to go supersonic speeds without that vacuum. And the reason it's important to have that vacuum is because there's nothing in the way. There's nothing to keep the ping pong ball from accelerating. And that's the basic principle behind evacuating with a pump the air inside the exhaust of the turbine. So we've got 2 stages here. As everything expands, it takes up more space. So here's the turbine. This side's the turbine, this side's the pump. Tesla says 3 times the volume on your pump, because as the air expands, it takes up more space.
So how many discs are on the drive stage and how many are on the pump stage?
There's 11 on the turbine and 33 on the pump. And just so everybody knows, when you couple the turbine and the pump, you want your pump to have a larger diameter, so that your periphery velocity is maintained under load. So once you load the turbine down, the speed of the pump also reduces. But you don't want your periphery velocity of your pump to reduce, because that reduces the pumping action.
And these are the same diameter, obviously.
Yes, they're the same. They're the
So,
same diameter. And
ideally, it would be larger.
Yes, this is an older design, and that's, yeah. And then also, if you want to even upgrade it more from there, you would have another pump on the other side of the turbine. So you'd have pump, turbine in the center. But just because we have this one here, just to show you how everything works, I'm just going to go ahead and describe what we've got here.
Okay, I'm going to bring the camera up close so we can look at each of the parts. Okay, so here's the drive stage and the pump.
Turbine pump.
Okay, and you got end plates and then the center plates. Do you want to explain the difference between those?
The end plates on this side, because we've only got one pump, has no holes here, because you don't want the air to go in the turbine, spiral around, and come out these holes. Keep that blocked off. But on the other side, you can see it'll exhaust out the center right here, and then you have an open channel connecting the pump stage. And because there's two of these rings right here,
so that directs the drive.
That directs it right into the pump.
Right.
So internally, all of these holes right here go all the way through all the discs, and then there's star washers that separate the discs that allow the air to come out.
And these are close to 1/64 of an inch spacing?
Yes, these are close. They should be 1/64, ideally, for steam. And there, you can also see another problem here, an issue where the gap between the separator is too large. Ideally, you want a smaller gap than your discs. Now, you don't need a smaller gap than your discs, but the closer you can get it without it hitting, the better. So then this ring goes over that, and that makes a channel between the two, like that, which separates which prevents the air from going straight from the turbine to the pump and bypassing it.
So when this channel piece here is locked with the other piece, it spins with the entire assembly.
No.
It's stationary.
This is the ring in the middle. It's stationary.
Okay, so it gets locked on with the housing.
Yeah.
Okay.
It fits right inside. So this is the turbine housing, and this is the pump housing. And you really don't even need a pump housing. You really only need the turbine housing. But if you want to direct the air, which is what is our original plan here, you've got an opening.
And you have two or three extra holes, right? Just to get a little bit more.
I needed to open it up.
And
you can completely get rid of it.
Sure.
And that would be the maximum efficiency, to completely get rid of the casing. But then you need a vacuum chamber around your turbine, which is fine. It makes sealing everything up a lot easier. So we've got our inlets here and here, dual inlets. Dual inlets help because you can have a larger inlet for more power without making the dimensions out of place. So you don't want your nozzle to be too fat. You want it to be small enough to where that boundary layer, the dimension is more efficient. So yeah, you got your inlet nozzle here, two nozzles. Tesla later on said he found it to be more efficient with more than one nozzle.
Which can be air, steam, whatever.
Air, steam, any gas. In fact, we're going to use lithium chloride methylene chloride because it has a boiling point of 100 degrees. Now we've already got the turbine to run on 165 degrees with just pure water, and that's under vacuum. So that's actually water boiling under its boiling point because it's under vacuum. But with the methylene chloride, you get an even lower boiling point.
Which is the red drinking bird fluid.
Yeah, they've actually got they've got the red drinking bird boils with atmospheric heat and actually causes the bird to tilt and take a drink because the pressure that's created at the bottom pushes the fluid up because it creates pressure with the gas. It pushes the fluid up, and it's heavier at the top. And you can, if you type in the drinking bird on YouTube, you'll have a better description than what I just gave. But that's the basic principle.
Yeah, you wet
there.
the head and it comes up, cools off.
Cools off,
And then,
it comes back down. And so that's the basic principles of that. So if we do, should we somewhat
Do a assembly?
should we?
Yeah, you want to talk about the bearings first? What kind that you have in there?
These bearings are a hybrid bearing. It's a hardened steel race with silicone nitride balls. And we've also got ones that we're going to try.
Like $75 a piece.
No, the $75
Okay,
ones
that's
are these ones.
Okay.
These are the race is silicone nitride and the balls, and because they're about the same hardness, you won't wear out the hardened steel, because they're so much harder than hardened steel, surprisingly, that you will wear out your hardened steel race, and then you'll get a side-to-side movement of the rotor if you're not perfectly balanced. But you do want it's extremely important to get your rotor balanced really well, and then you won't wear out your bearings very fast. But then there's also one more thing you can do. You can add a rubber race around the bearing. I'll just pull one of these out so I can show that. So you put a rubber race all the way around your bearing, and what that does is it creates dampening. It's, for instance, an analogy, if you were to put a rubber mat on the floor and drop a glass jar on the rubber mat, it's more likely to, it's less likely to break than if you were to take that same glass and drop it straight on the concrete. So, and it's the same principle as your tire. In your
dampening.
The reason we have tires, the rubber that goes around the rim of our car, is so that when we're going along and there's all that vibration, you don't want two hard surfaces running against each other. So if you put that rubber race around there, even if you're not perfectly balanced, you will get that dampening and your bearings will last exponentially longer. In fact, in turbochargers, they use that rubber race or a flexible race around the bearing. It doesn't necessarily have to be rubber, but they use that with ceramic bearings. So this is completely ceramic, and this will be the most frictionless bearing that you can get, but you have to have a balanced rotor, and you have to have some protection against that vibration, otherwise you'll wear them out. You got the rotor here, turbine, the pump. You put your ring in between the turbine and the pump, and I've got a little marking that shows the right direction to put it on. And once your ring's assembled, take your turbine side or your pump side. This is the turbine side. Snap that side in. Snap the other side in. In this particular one, you line up these holes right here. Mm-hmm. That's for your base plate. And then that's pretty much it. And then you just have to put the screws in. So I'll start with
It's a beautiful machine.
Yes, it's mostly my design, but I didn't build it myself, and I had my machinist made a couple suggestions that were really nice, including that ring in there, that made it all come together pretty well. And of course, Tesla designed the discs and the turbine and the pump separately, and he suggested that you put them together. There's two ways you can put them together. You can put them on separate shafts, but then you have to have a motor drive the pump, which is great, but it makes it a little more complicated. So I started with the easiest thing that I could start prototyping with, and that's the turbine and the pump on the same shaft. But the biggest thing that the biggest thing you want to realize is the pump. If they're both on the same shaft, the pump needs to be larger in diameter. Otherwise, you'll just get a little boost in efficiency. It won't be as dramatic. Because once you start adding that load, the pump slows down, and you want that pump going maximum velocity all the time. And if you got really good bearings, then the pump can go all the time without losing much energy to the bearings. And our latest advancement is actually air bearings.
And you have these videos posted on your channel.
Yeah, I posted them on the YouTube channel, and also on Patreon. You can get the latest updates to what we're doing, and our latest video is on Patreon on the air bearings. They're surprisingly easy. Applied Science is actually the guy that gave me the design, or that gave me the idea, and I think he said he got it from someone else. I'm not sure.
Now, out of curiosity, are you planning on opening up a channel like on Gab.com, or putting your videos up on BitChute and some of these other channels? Because
I've wanted to for a while now.
Yeah.
I need to get that done. I'll put the link in the description on my YouTube channel when I do get that done, so you can go straight to there. And if you join the Patreon, I'll also have the links there, of course. But yeah, if you join the Patreon, you'll get access to all the content early and behind the scenes and extra content.
Right.
So. And
then for 2021, assuming the world continues as bizarre as it is, planning on the 10th annual Energy Science and Technology Conference in Coeur d'Alene, Idaho. I think the second weekend in July. It'll be Wednesday through Sunday. Planning on 5 days. And if things are normal, whatever normal means, but if we can still have that conference in person, then you're planning on having another presentation there.
Yes.
With
a demonstration.
With a demonstration.
So I've got 3D printers now. I can make everything in house, so I've been able to make things faster and exactly the way I want it. If I need to make an adjustment, I can quickly 3D print it. And so, pretty optimistic about having the full Crafter system running at the conference this year. So, and then you just put the end plate, or the end pieces here that hold the bearings in place. I've taken this apart quite a few times, so and my machinist did too. So these are a little stripped, but or actually I should just probably screw these all the way in.
Are those metric or standard?
I don't know.
Number 10, we probably have.
I think they're probably metric, but it's a good question.
Because we have a bunch of stainless.
Oh yeah, you don't want to fully tighten down one side before
I
you got the other.
I don't know if we have the Allens like that to fit in the holes. We'll check.
Oh yeah, these are the right Allens for these bolts.
Oh, I mean non-stripped ones. We might have a whole supply of them.
Oh, of bolts.
Yeah,
okay.
We have tons of hardware here. Yeah, it's a little tight.
Yeah. It's not going to come out, which is great. You don't want them coming out. But you also don't want to strip them.
So for the average experimenter out there who's interested in the Tesla turbine and the pump, would you say that the simplest thing for people to do is to download some 3D printed versions just for some low speed tests and blow some air into it, just to kind of learn the principles? What would you recommend for the beginner?
Absolutely, and I'm getting better at making or spending more time making the instructional videos to show how everything's made and constructed. And I've got all my latest designs.
Have you made any 3D printed 3D printer files available, like through Patreon or something like that?
Yes,
people
Patreon
can download
there's the CAD drawing tier. It's tier 3, It's got all my latest CAD drawings. In fact, it's got the larger pump.
Mm-hmm.
Um,
So you can just export a STL or
yeah, we got STL, and we're also getting step files on the new files. So you can go step or STL. But the STL files you could throw right in your 3D printer, and then do what I do, do what I show.
And obviously that's just for learning purposes, just to kind of see how the thing works. But,
and it's interesting because if we use ammonia if we mix ammonia with water, we can bring the boiling temperature way down on the working fluid in our hot tank. And we might actually be able to get away with just using plastic as actual 3D printed turbines as our final model that you can make functional, that will be functional. But you could, if you want it made out of metal and you want to run higher temperatures and you want to get higher power out of it, you can give those 3D printed parts to a machinist, and even if they don't know how to use CAD files and stuff like that, they can look at the physical turbine that you printed out and make it out of metal. We're using carbon fiber, and we're also going to test fiberglass. It's all about the weight of the material and not the strength. Carbon fiber can be 2 times lighter than aluminum, but it's way stronger. It's stronger than steel, and its tensile strength is what really shines. So not only do you get a way lightweight material, but you have a very strong and very lightweight material, which is the best mix ever. So you can reach higher peripheral velocities. You won't have to balance your rotor as much right off the bat. But I will be showing how to balance the rotors with a pretty simple setup in the future too.
So once these screws are in and mount it to the plate, we can probably blow some air through it, just kind of show it spin a little bit.
Well, these nozzles are really big, and we're gonna have a really big.
I'm gonna have to go crazy with it, but just to show that it.
Just to show that it spins.
Yeah.
Yeah, we could do that.
Yeah.
We could do that.
Okay.
But yeah, for a small air compressed system for testing, you're gonna want smaller nozzles, so that you get higher velocity and at lower volumes. So we won't be able, with these nozzles, we won't be able to show very much.
Okay.
But we can spin it up just to show it. Do you have an RPM meter?
I don't think so. Not in here.
Okay. Well, we could still run it up.
Yeah.
And then that goes right in here.
Where's the screws at?
Did I do it wrong? Here we go. So building everything out of this kind of material is going to allow for very high temperature and very high power and high pressure. So this would be pretty incredible if you started using, say, superheated steam. You could really show the extremely high power outputs. Tesla was predicting or got 10 horsepower for every pound of weight.
Didn't look like that screw threaded.
It didn't. I think it's too short. In fact, I don't think either of them did. Here's one. Okay, so it was long enough. Sorry, I used the wrong.
Are these number 10s? I don't know if that's long.
Yeah, that might be. Yep, there we go.
Got it. Now that'll make it nice for mounting inside of a box.
Yeah, for sure. And so it needs a spacer on this side. These are my machinist's old bearings, and he did run them a little bit. And what I did after I ran it and wore them in, I put a spacer. I put a spacer in there to keep the gap at the right spot. Because see how it moves back and forth? Because those silicone nitride, the silicone nitride was wearing the hardened steel. And if this was balanced better before I ran it, and then it wouldn't have worn those bearings. And if they had rubber races, heck, this thing would have lasted for months running it, or even years.
Okay, so we're not going to get it up to any crazy speed. This is just to show where the input goes into the drive housing.
Yep, there's one here and there's one on the other side. So we can either go in this side, or we can go in on this side.
And you'll see those discs start to move.
We definitely want to plug one side so that we don't leak air. Sucking in really hard. That's really weird. It's pulling right now. The pump stage is drawing in from the turbine stage.
Yeah, say that a little bit louder.
The pump stage is drawing air in from the turbine stage. And that's the effect you want. The stronger this effect is, the better it is.
It's blowing out.
That's what I was talking about the other day. The Venturi nozzle. Actually makes it more efficient to use let ambient air assist the draw. particular one about 32,000 RPM. So we didn't get anywhere near that.